There. Okay. So now we have the element stiffness matrices and the element force vectors for both elements so we can assemble them. So first we allocate the space for the global stiffness matrix. How big should it be? Huh? 9 by 9. And for the global force vector, 9 by what? There you go. So then we just have to put them into place. So K. Now I know in the past you guys have seen me do stuff like, so we want the first element stiffness matrix to go in that right hand corner that's going to go from 1 to 6, right? In that submatrix. So in the past you've seen me do stuff like 1, 2, 3, 4, 5, 6. But in mathematical, there's another way to do that where I don't have to write them all out like that. I can just say range 1 to 6. So those are equivalent, so I can just leave it like that. So if I put KE1 into that location, and then do the same thing, range. This time I'm going to go from 4 to 9. I'm going to put KE2 in that location. So if we do that, then we can look at what K is. All right. So, we're only looking at 1, 2, 3, 4, 5, 6. So there's three more elements off the screen this way that you can't see. If you made the font smaller, you could. But you can already see this is just 2 elements, and look at this. Do that by hand, right? It's going to be horrible. All right, so we can also do the same thing for the global force. This time we're going to go from 1 to 6. From 4 to 9. And if you want to take a look at that, we can. All right. So now all that's left is to apply the boundary conditions. Okay. In this case, there's still that one force that we haven't done anything with because it's applied at a node, this one. And like you mentioned on the board, this should actually be 2p. Okay. So if we go ahead and apply that, now can anybody tell me to what degree of freedom or where in that F matrix that's applied? Which direction does it act in? The Z direction. At what node? So what deformation does that correspond to? U is the X acts in the X direction, W acts in the Z direction, right? So that would correspond to W2 is where we'd want to apply that, okay? So in the global force vector, W2 is in the 5th location, right? If you look at that where I wrote down those unknowns, count down to where W2 is, it's at location 5, okay? So we'd want to apply that boundary condition there. We'd say F element 5. We want to add to whatever's there 2p, okay? So now if we look at these, this is now 6p, all right? So we also need to take into account the fact that we need to impose the other boundary conditions, the displacement boundary conditions, or the essential boundary conditions. So that means that U1, W1, theta 1 are all 0. Same thing for U3, W3, theta 3. They're all 0. So what we can do is just drop those from the K matrix, right? So the way I'll do that is I'm going to say drop the first 3 rows and the first 3 columns. Okay. Then I'm going to say drop the last 3, and mathematically you can count from the end by saying -3. So I'm going to say drop the last 3 rows and the last 3 columns. We'll call that K new. And I can do the same thing for F. Call it F new. I'm going to drop the first 3 and the last 3. And the K is just one-dimensional, so I don't have to do all this transpose stuff. Okay. So if I do that, then we can see what K new and F new are, and we still have these EIs and EAs in there. So I'll go ahead and plug in some numbers at this point, and I'll say EA is E is 10 to the 6th times A, which is 10, and then EI is 10 to the 6th times 10. Okay, so I'll go ahead and do that, and then now we're ready to solve. So we just say linear solve K new F new. And I made a mistake somewhere because that's not the answer.